There's beginning to be an understanding that we want much more foundational or general AI models that we can use in science. There's almost this notion of artificial general intelligence for science.
So now it's really not just that the model is accurate within 90%, is that the model is accurate with 90% probability.
Physics-based simulations being replaced to some degree by surrogate machine learning models.
There's another approach that people are thinking about that's more radical, which is an end-to-end solution.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hi, I'm Doug Black, and again, I'm with Shaheen Khan. Great to be with you. And today we have a very special guest. We have Rick Stevens from Argonne National Lab, and our special topic today is AI for science. So, Rick and Shaheen, welcome.
This is such an exciting topic. Thank you, Rick, for making time. Great to have you.
Thanks.
So, Rick, when simulation was the new thing and supercomputing was in its earlier days in science, there was a really big focus on how we started out with theory and then we added experiment and Galileo came and all that. And now, over the past 10 years, we are digitizing science and we are applying simulation as a net new tool, and it was positioned as a third leg of the stool. Then with the advent of massive amounts of data and now AI, how do we position that?
You could think of it as a different way of weaving the stool, maybe. So we have theory, and many simulation codes or problems that we use simulation for, there's really very little experimental data in those simulations, right? We kind of simulate from first principles. And in theory, especially in, say, physics, quantum mechanics and so on, we have very, very high confidence in that theory. And we can build simulations with just a bare amount of foundational data, and the models can be quite accurate. And so in places in science where that's the case, we still do that. In many areas of science, we don't have strong theory. I mentioned this before, but like biology, for example. We have a lot of understanding of aspects of biology, but we can't build a predictive model of a cell in general. We can do it for some cells maybe, but we can't do it in general. But we can make lots of measurements. So this idea that we can build models directly from the data without an intervening theoretical interpretation of that data is the difference, right? That's the new thing. Machine learning gives us a basis for doing that. There's, of course, lots of different ways to do it, but the basic notion is that you're going to train a model, you're going to build a model, it's going to be exposed to thousands or millions of data points, and at least within some space, it's going to be able to make predictions that are pretty good. And we can test, in general, we can test against new held back experimental data and so on. And we've gotten pretty good at building these kinds of models. If you have an environment with theory, experiment, and simulation, now you have this ability to create new types of models. For many applications where you would use a traditional simulation based on theory, you might be able to substitute a different kind of model, and that might work in some cases, or you might augment your simulation, or you might replace the simulation entirely. But there's other ways of using it. This is something that maybe people haven't fully appreciated yet. So I would say that in addition to this narrow notion of AI, that is for each problem, we collect data and we build a model and we can use it to make predictions in that narrow space, there's beginning to be an understanding that we want much more foundational or general AI models that we can use in science. There's almost this notion of artificial general intelligence for science. An example of this would be, say, a large-scale language model that's, say, trained on all the scientific literature. And then you use that model maybe to generate hypotheses. Many people are starting to think about that. Or a model that might be trained on, say, lots of mathematics, and you then use that model to conjecture new theorems. So don't think of AI for science as in this very narrow sense of just building a model around, say, structured data that we might get from an experiment, but it might be the idea that we're trying to automate, in an AI sense, the very underlying reasoning that we do in science. Does that make sense?
So it's a much more versatile tool than it might appear at first.
Yes, I think that's correct.
And maybe far-reaching tool.
Yeah, far-reaching in the same way that AI in general life is likely to be very far-reaching.
Okay, so that's really very interesting. If you gazed at the stars and you looked at the motions, that's data. And if based on that data, you came up with gravitational theory and then you observed it and it all seemed like, yep, that seems to be nailing it. There's an exactness to that theory, that model, that seems to be lost when you go with massive amounts of data and you become probabilistic. So now it's really not just that the model is accurate within 90%, is that the model is accurate with 90% probability. To me, that's a fundamental shift in how the accuracy and the precision of the models operate. Is that true? What is your perception on that?
In the example you were using, if you were talking about Newtonian gravity, of course, we know Newtonian gravity is not correct. How you would throw a percentage on it depends on the problem you were doing. If you're trying to model black holes with Newtonian gravity, you might get the wrong answer.
Good point.
I mean, we have this notion because physics has been so successful, particularly prior to Einstein. Newtonian
Right.
mechanics was very successful, and quantum mechanics, of course, has been incredibly successful. We don't know how to bridge between quantum mechanics, say, and the standard model. So we have big holes there. And I think, again, if you're thinking in terms of the small cases, right, where I have limited training data and I'm just building a local approximate model, of course, what you say could be true. That is, the model makes a probabilistic statement about the world. Now, of course, we can formulate these models to emit precise statements about the world. Like, here is an equation that predicts X, and people are doing that. We can use AI to, say, integrate a complex equation, and it produces an exact answer. So it doesn't have to be this fuzziness sense. I mean, probabilistic reasoning is part of what we're talking about, but it's not the only thing we're talking about. There's been some recent results that are kind of fascinating where people trained a model on this is like recurrence relations. So they generated a whole bunch of data mathematically, trained models. The models got the wrong answer. They got maybe some fraction of it right, but they kept training. And after something like 10,000 epochs, suddenly the model got the exact answer. In other words, the model eventually solved the problem precisely, because you were kind of trying to get the model to learn an algebraic relation, and eventually it figures it out, right?
Right, right.
I'm not trying to generalize from that necessarily. I'm just saying that I think there's a lot we don't know about how we're going to use AI in scientific problems.
Yes.
Some problems, having a probabilistic estimate is a step forward. In other cases, it might not be, unless it was maybe orders of magnitude faster. In those cases, you might decide, what can I do with a model that's maybe only 95% accurate, but it's a million times faster than my current method?
Actually, that's a good segue into the article that Doug, you wrote.
Yeah. Last August, it was really based on a presentation you gave, Rick, but this notion of physics-based simulations being replaced to some degree by surrogate machine learning models. I guess my question to you, is this a new means of a workaround to very expensive compute-heavy physics-based simulations, or is it just an adjunct of this whole AI for science movement?
Certainly a leg in the AI for science space. When we think of AI for science as having these problems in design, like molecules and stuff like that, surrogates is one of those. We think of autonomous labs. We think of AI being used to write code for supercomputers as another one. But in the case of surrogates, the way I think about it is, and usually what's being done is, where you have some existing simulation, and it might be perfectly fine. It might be a density functional theory model, or it might be a fluid dynamics model, or an earthquake model, or something like that. And what you're trying to do is you're trying to figure out if you can replace a computationally expensive kernel that may be at the heart of the method with a much less computationally expensive replacement, i.e., the surrogate concept, that is trained on data that might have been collected by running the expensive model on various problems, and then generating your own training set, training this replacement model, and then plugging it in, and using that in many scenarios where the output of that model is within some bounds of accuracy or performance that you like. And this is being done increasingly in broad areas, in fluid dynamics, in quantum chemistry, in material science, density functional theory, in virtual drug screening, which is what we've been using it for, in climate models and other things, earthquake simulation, cosmology, and so on. And people are seeing speed ups anywhere from factors of 1,000 to factors of millions, hundreds of millions, or even a billion in a
Wow.
few cases.
Hmm.
And the speed up is coming from the computational complexity of the machine learning model when you're running it in inference mode being, substantially less than the complexity of the underlying physics-based kernel that you're replacing. That's where you're getting the speed up.
So I'm going to say just, but I know it's a very significant thing. Is this just interpolating historical data to get close enough to the destination and then do the last mile with the exact model?
In many cases, that is the approach. So in quantum chemistry, where you're, say, trying to find a molecule that has certain properties, and you're trying to search, say, millions or billions of molecules, so you would put a fast method in, you would search as fast as you can, you'd find things that get you close to the thing you're looking for, and then you would go back and, say, run the original method, the more accurate method. That's one use case. But other use cases, you don't go back. So, for example, in climate, we're often interested in doing ensemble simulations of climate because we want to understand how much variability there is in the climate or how much variability there is in hurricane tracks or whatever it is that we're simulating. And there you might be willing to say, if I have a surrogate model that, say, is 100 times faster than the original climate model, before I might be able to afford to run, say, 10 instantiations of the climate model ensemble of size 10. If my individual model is 100 times faster, for the same cost, I could run 1,000 models.
Uh-huh.
And 1,000 models would allow me to estimate things a lot more accurately than 10.
So are you saying this could have tremendous potential specifically within climate?
Absolutely. This past fall, there was a community-wide series of workshops called AI for Earth Systems Predictability. It was sponsored by the DOE Biological Environmental Research Office. Over 1,000 people participated in that workshop over 2 months. And this was one of the kinds of questions they were asking about where AI can impact climate processes, climate forecasts, climate understanding. So this was just one of the scenarios, but there's many others. I mean, for example, climate models right now, when you run them, produce terabytes or petabytes of output. And no human can sit there and look at all that data
Right.
to look for anomalies or to look for patterns. And so even if you're not replacing the core of the climate model with an AI component, there's a lot of interest in using AI to actually process the output, to look for interesting things, or to project from the actual fields that the climate model simulates to things we actually care about, like rainfall or flooding or something like that. So this idea of using AI as a bridge between, say, simulation and impacts understanding is another use case.
Interesting. Maybe we could say that when it comes to climate science, we've gone beyond our last AI winter.
Haha, yeah. We hope. Or maybe we can use AI to steer us back to real winters. Or something.
And by the way, are there bigger models in existence than these climate models? Are they the mother of all models?
Yeah, well, there's actually several groups that are building these AI-enabled climate models. I would say that it's still pretty early in the sense that there was an attempt last year. I should preface this a little bit in saying that there's a series of strategies for doing this, right? One scenario is you go in and replace individual physics components one at a time with an AI model, okay? That's a very discrete kind of surgical operation where you pick a particular atmospheric process and you replace each one separately with separate AI models. And there's been a lot of work doing that. And in those cases, you have, benefit that you get, but it's a lot of engineering work. There's another approach that people are thinking about that's more radical, which is an end-to-end solution. That is this idea that you would take raw observational data, say of climate or weather patterns over the last 100 years, and raw satellite data, and you train a model to take that data and make a forward estimate, train an AI model to make that forward estimate. In other words, there's no traditional component in this system. It's just a pure AI system that's end-to-end trained to predict the climate from whatever training data you give it.
It's almost like a recommendation engine.
Yeah, kind of. And there was an experiment done in Europe. I guess maybe UK. It's not Europe. I guess they don't consider
Right.
themselves part of Europe anymore. But anyway, this model worked. I mean, it wasn't as accurate as the current model, but it was a first effort. But the fact that it worked at all was pretty amazing, right? This notion that we might replace an entire pipeline, an entire way of doing business in some sense with an end-to-end trained AI model is kind of amazing. And it's that idea that's revolutionizing many, many other areas of technology where you're replacing with AI. For example, Google's experimenting with using, a single end-to-end AI model that replaces the entire search infrastructure. So things that might have dozens of components that talk to each other, just replacing all of that with one model, that's an idea that's out there. And we think that it is showing some promise in various areas of science, but it's still very early.
So is this like atomizing an entire workflow? Is that the idea?
I don't know if I'm atomizing it, but
Compressing.
yeah, compressing it into one box. Think of a workflow that has like a dozen, and saying, we don't need no dozen steps. We're going to make one step. We're going to do it all in one leap. Yeah, that's the idea.
Tremendous potential then.
I think so.
I know, getting back to climate science, the Wall Street Journal recently ran a big piece that I also featured, that when it comes to certain parts of the science, the modeling and the use of supercomputers just is not getting there, and real frustration. So maybe some of these techniques you're talking about could provide something of a breakthrough.
Yeah, I think so. I mean, climate community is generally pretty conservative, and we want to get it right. That means trying lots of things and being very careful in how one validates any alternative approach. But these ideas are showing promise. This concept of an AI trained model, and whether you're doing it in climate or in materials design or in medicine or whatever, they're showing promise. And we have to try. I mean, we owe it to ourselves and to the reason we're doing this in the first place to try these things, right? I think it's not going to be a simple, yesterday we did it one way and tomorrow we do it a different way.
Yeah.
A good example of how this works is in, say, the protein folding problem. So if you looked at what DeepMind did with AlphaFold 2, which is the current system, that they finally released that essentially can use AI to solve the protein folding problem to first order. I mean, it solves it. That's not a single model. The current version is not a single model. It's actually several models, plus it's got some traditional bioinformatics in there and so on. So it's a workflow, right? But that workflow just didn't pop out of the air. It was built out of many, many years of research and trying many things and failing often, and continuous benchmarking against the traditional methods people were trying to use. And at a certain point, we had enough data, we had enough compute power, we had big enough models, we had enough ideas that it started to work. And I think that that's the lesson, right? The lesson in many of these, across these areas of science, is that there's some combination of existing understanding, existing methods, accumulation of more data, models that show some capability to generalize, and the ability to integrate all of this and to train it, which needs a huge amount of computing. It's the combination of all of that that's going to result in this notion of AI for science making impact.
It's an incremental struggle, in other words.
It is, but it's also incredibly computationally intensive. And I think that's the end of the day. This is not going to save us. It's not like suddenly we're going to use these AI methods and we're not going to need supercomputers. We're going to need even more supercomputers.
Right.
Both for training this, but also because we're going to want to expand the scope of what we can do.
Our conversation with Rick Stevens continues. Tune in next week as we touch on ethics, bias, security, and explainability in AI and exascale, and whether AI will replace scientists. See you then.
That's it for this episode of the @HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.